received his bachelor's in China from Haozhong University of Science and Technology. Today, Yu is going to tell us about the assessment of railroad ballast in a life cycle behavior.
Thank you. Yeah, I'm very honored and humbled. Or something which is not a lot of related with highway pavement, but I'll talk about aggregate behavior in railway ballast. So the first questions coming to our mind is why we want to do a research on ballast behavior. The thing is that the ballast is an essential layer in railway structures, primarily provides load distribution and drainage. This layer is the first layer of railway track substructure, and it's very important, directly contributes to railway safety, comfort, and reliability of the track. A lot of problems can happen for this layer. And if that happens, for example, this is a photo shows a case of fouling and pumping. This is buckling because of lateral stability, failure of the ballast layer. And this photo shows the excessive permanent deformation or settlement in the field of the track. If this kind of problem happens, we have to stop the train, fix the problem. Will cause a lot of delay and a lot of problem, and lose a lot of money and time. And recently, in the United States, we made a new challenge. It's called a SHEAR corridor. We not only have heavy axle load or freight train, but we also want to have higher speed passenger trains. The combination of these two completely different cycle loading will cause more challenge of the track structure currently we are using in North America. And in the world, there are another kind of mixed traffic. This is another kind of shared corridor in China. So with the track designed for high-speed passenger rail, right now they try to introduce higher speed freight train into the current track. This is another mix of cyclic loading. And previously, we did a lot of research on ballast track. However, most of the research is based on continuum approach. This is something was done in University of Illinois, date back to 1970s, to analyze. This is a software called ELITrack, developed primarily by Professor Thompson and his co-workers. We can have a lot of this kind of software before, but most of them based on continuum approach. However, from appearance, we can understand the ballast layer is not a continuum medium. It's comprising of discrete particles, the ballast. And throughout of the life cycle of ballast, the particles will have significantly change in grain size scale, the gradations, distribution, and also the particle shapes. This is a picture is real happened from Canadian National Railway. After 10 years, without much maintenance, we can see clearly how the particles change. So since they change in grain size scale, what kind of performance they will provide 10 years later? Will they provide the same performance? Probably not. So that's a motivation. What are we trying to do? We try to develop a framework in this study which we can assess the life cycle behavior of ballast. In this one, we try to integrate the multi-scale, which means we have micro scale to characterize ballast particle shape per case and grain size distribution. We also try to integrate the laboratory testing and field performance monitoring. And also, not only from experiment part, we also try to integrate numerical simulation, which were based on, mainly based on discrete element method. So to let you have an impression again, we're not only targeting on at the beginning of ballast life cycle, but also we try to tackle the behavior at the end of their service life. This is another picture to show you the objective of this study. We try to develop a multi-scale, integrated experimental and numerical simulation framework. The specific tasks for assessment of the life cycle behavior, we first of all focus on the beginning, which is new ballast life. It's kind of like new material we're going to put in a new track. First, we will do a large-scale TRIAXIAL test mainly focus two aspects. One is monotonic compression test, which can give us evaluation of strength behavior. Another one is repeated loading test, which will give us permanent deformation behavior, which can connect with the field settlement. And then next step, we will do a field validation to see how this approach works or not. Next step, we will do a field application. For example, this is a picture taken in an Illinois track. And we can see clearly there's a differential settlement between the embankment and the bridge deck. So how can we tackle this problem? How can we solve the differential settlement in the field with this framework? And then move to the next step. We'll try to characterize how the ballast change from the beginning of its service life towards the end of the service life. What happened in between? So we'll use like laboratory study of ballast fouling by particle degradation. And then when we move to the end of the ballast life cycle, we use a fouled material to do the same thing. First of all, large-scale triaxial test to see what is the strength behavior, what is the permanent deformation behavior of this kind of like residual material ballast life. And we'll also think about how about if we have reinforcement? Is the reinforcement performance the same at the beginning of ballast life and at the end of ballast life? And how that will change the deformation and the strength behavior of ballast particles. The reinforcement we primarily use will be gel grade. And also we'll think about what about if it rains? Will the ballast material behave the same when it was wet and dry? What about the change of a wet new ballast material and a wet fouled ballast material? Will they behave the same? The specific tasks we'll talk about is, first of all, look at the new ballast material. From grain size scale, we will analyze the particle shape properties and do strength and deformation. And then move to the field validation, move to the field application. And then use LA abrasion test to do the laboratory task, and also move to the end to see the same behavior. I think I already covered it pretty much, so I'll skip these several slides. So, large-scale triaxial test. This is the large-scale triaxial test device developed here, dedicated for testing ballast size materials. As I mentioned before, we will try to study both the strength behavior and also the deformation behavior. For the strength behavior, we have like various of confining pressure. For the permanent deformation behavior, we'll try to use like a customized cyclic loading instead of continuous sinusoidal loading waves. This equipment is very comprehensive. We have like a Honeywell mode to measure up to 20 kips loading with the loading pressure. We have 3 LVDTs wrapped 120 degrees around the specimen to test the deformation at the central part of the specimen. And then we can have average value just in case the specimen gets tilted during the test. We have another circumferential chain wrapped at the center of the specimen, try to measure the radial strength of the specimen. So the first step, we go to the lab and try to see what is the gradation, what is the shape properties with the sieve analysis and image analysis of the particles. And then we're going to relate this one with the macro scale ballast behavior. This is to show the test result of the gradation analysis and also the image analysis of the particles. The way we construct the specimen is to use like 4 equal lifts, and we apply uniform compaction to each lift. And each specimen was compared with the same compaction time, which means the same compaction energy. And here I will show you a video to show how the strength test So this is monotonic compression test. The strain rate is 5% per second. So in 2 seconds, it will reach 10% strain. And we also used another strain rate, which is 1% strain per minute, which is typical approach of geotechnical testing. And interestingly, one of the key findings we figured out is there's no difference, or there's no significant difference if we use different strain rate. So this kind of material is not sensitive to strain rate. No matter what kind of confining pressure we use, they all provide similar results. But here comes another question. Since we construct the sample and put it into the lab to make a test, since it's discrete elements, we cannot guarantee for each test we are having the same particles in the same position. In other words, if we have exactly same particles, if they have different arrangement, how much the variation can be? That is a question. So we did repeated test with the exactly same particles. Like after one test, we reclaim all the particles carefully, just in case we lose a lot of materials. And then we put the same particles to construct a sample again, try to see the variabilities. And after several tests, we keep tracking of the gradation change until a point the gradation changes significantly, and then we cannot consider they are the same particles. So we finished the 3 tests without significantly changing the particle gradations. We can see there is a variability of the same particles to construct the same geometry of the specimen. And this phenomenon will be studied later on with discrete element method. And moving from the strength test to the permanent deformation test, we use a load which has a rest period between the loading pulse. This is based on there is a distance between the axles of the train. So the 0.6 loading duration and 0.4 second loading duration and 0.6 rest period is based on currently typical operation speed of in North America was about 45 or 40 miles per hour. So a 20-meter length car gives us 0.6 second rest period. And we load the specimen up to 10,000 cycles to see the permanent deformation behavior. This one can be related later on with the settlement behavior. And we will see with the same particles, there also has a variability. But by average of the 3, we can have a general idea of how the deformation behavior happens. So that's the experiment part. How can we simulate this? The challenge is if we want to use discrete element method to simulate this kind of discrete behavior, the first main challenge is time and computational expense. In order to capture the details of particle contacts, we have to use a very small time steps. And this gives us a higher requirement of the number of iterations. And also, when we do the experiment of large-scale triaxial test, we use membranes. And we know after the specimen fails, we will have a bulging at the center of the specimen. But how can we capture the bulging? That's another challenge. Previously, based on the literature, somebody used rigid walls or rigid boundaries and that can moving, try to simulate the bulging. However, that approach cannot give us the similar shape. They only can give us the volumetric change. We want to capture the exactly shape. And also, for all kinds of numerical simulation, we need to calibrate our parameters. For example, in FEM, based on my knowledge, I think there are about 13 or 15 parameters we need to calibrate. For discrete element method approach developed here, we mainly need to calibrate contact stiffness and interparticle friction angles. So first, to solve the flexible membrane, this approach was first proposed by Dr. Li, who graduated this year, to use the discrete particles to bundle them together to simulate the flexible membrane. So each particle can move in radial directions while the movement of rotation and in other direction is restricted. This approach can be further, how do you say, if we want to get the exact shape of the particle specimen bulging, we can make the element infinitely small, and then it will be kind of a real shape. However, that will infinitely increase the computational expense. So there's the optimal solution to use the right shape of or geometry of each element to give us approximate shape of the bulging, but still make the computational expense manageable. For the based on that approach, we work together and propose this kind of like model. We use 8 layers of membrane elements and then 12 elements in each layer, so totally 96 discrete elements to hold the specimen to simulate the membrane behavior. We use exactly the same geometry as what we use in the lab, which costs us a lot of computational power, and exactly the same confining pressure. In another word, we're simulating the same thing as a lab. The modeling parameters, Qian, Ks, which is contact stiffness, and the particle friction angle, or say 31 degree. These parameters actually are the same as my senior student who was now assistant professor, Dr. Huang. He used back in 2009. So we try to say for the same materials, the modeling parameters should stay the same. Otherwise, there's no meaning to calibrate those modeling parameters. Here's the overview of how the model looks like. The left side is to show the membranes, and the right side is to show the exact specimens. So here is a short demo to show how we can capture the behavior during the monotonic strength test. So if you look carefully, there's not only particle rotation and rearrangement, but there also some particle was dropping from certain height to next time step. So in this way, we not only can capture the macro scale, which like strength and strain in certain time, we also can capture the exact contact force and the number of contacts among the particles. And another important thing, as I just mentioned before, can we capture the bulging shape? The answer is yes. So if you look at this, we can capture exactly the bulging shape based on this simulation approach. And how about the result looks like? Yes, we can capture the strength behavior and in a fairly accurate. So this part was done. So next challenge is how is the variability of different samples? Was the variability the same in DEM simulation as the laboratory test? So we try to do the same thing. So we use exactly the particles, exactly the gradations, but just place the particles randomly in different initial arrangement, and it shows like a higher variability. So we will make a recommendation to do one simulation is probably not enough. To get a reasonable result, at least we have to have average of 3 simulations. Just try to address the variability of an initial arrangement. So this is the part of the strength test. How about the permanent deformation behavior? Can we simulate this kind of like loading pulse in simulation? The answer is yes, we can input any loading pulse. But the problem is when real time was involved, for example, there are 0.6 rest period. Do we just let the simulation run for that certain amount of time without applying any loading? Does that make sense or not? So with the same modeling parameters, with the same loading pulse, we propose a new method. It's called incremental displacement shearing method, which instead of while we shear the plate continuously moving down to generate the force, we're moving the top platen step by step. So we first move the top platen at a small increment displacement, and then we will check what is the reaction force on the top platen. Is it reaching the target strain or not? Or is it reaching the target stress or not? For example, in this case, our target divider stress is 165 kilopascal. So we first move it a little bit, try to see whether the reaction stress is 165. If we find the reaction stress is less than 165 kilopascal, and then we add another incremental displacement until the reaction stress equals to 165. And then we will move the top platen back with one incremental displacement to release the stress until the stress released to 0. This incremental displacement magnitude need to be carefully found. In case we load the specimen too quickly, which will easily above the target divider strength, or which will easily release the stress very quickly to 0. So we tried the several cycles. We will find the loading cycle between the incremental displacement approach was pretty much similar with the continuous loading process. And also that the assumption is based on what we find in the stress test, which means the strain rate is not significantly influence the particle behavior. Of course, we cannot load the cycles up to like 10,000 cycles exactly as the laboratory test. So we load the cycle up to 2,000 cycles. This probably took us a month or so for each case. And we have 3 different initial arrangements and average them. The average shows pretty much close with the laboratory test. And then we move to the field scale. The field validation was finished in 2010, which I have presented before, like last semester. So in this presentation, I want to introduce a field application. So based on previous study, we find particle shape properties and grain size distribution in micro scale does influence the settlement behavior in macro scale. And we find the particles with the lowest angularity has the lowest settlement potential. So think about the differential settlement in bridge approach. How can we solve the problem of the significant large differential settlement at a bridge approach? Do we want to have this kind of like a sudden change of the real profile, or can we do something to make the transition more smoother? Based on our previous finding, we propose approach to select the different ballast materials, which can give us different settlement potential, to let the differential settlement increase incrementally instead of one big differential settlement right at the bridge approach. So we get the ballast materials from 13 different sources in the United States. And we analyze from grain size scale of different gradation and also the shape properties. So based on this information, we select the 4 different materials to build the ballast settlement ramp, which we propose. And we run the DEM simulation to see and to confirm how this kind of like micro scale particle shape properties and grain size distribution will influence the macro scale ballast settlement in the field. And in this case, since it's a field application, the loading we used was 4-peak load, which was derived based on a model Dr. Huang was proposed in 2010. This is also confirmed by field measurement of the loading pulse induced by a real free train. Here, yes, sure, in this case, we include the real time, so it will give us like several months to run the same case to 2,000 cycles. In fact, we only run it to 1,000 cycles. So clearly we can say if the particles has a difference in micro scale particle shape properties and the grain size distribution, it does give us different settlement potential of permanent deformation result based on the DEM simulations. And then we called our friends in TDCI. We built the actual transition zone with the ballast materials we selected. This was done in 2012. And then They load the track with different ballast materials and figure out, yes, the settlement in the field is pretty much the same as we predicted from DEM. The only discrepancy is from one material, which is BM4. We figure out the reason. Why is that? Is because the quarry who shipped us a sample to the lab to let us analyze the grain size distribution and the shape properties, and then they changed their crusher. So they ship a different material to the field site to build the sections. That's why we cannot capture the settlement from the field of the different materials. Okay, so that's all for the clean ballast materials, which were considered as newly constructed track. But we still have the problems. This is what happened in the field. Probably most of the track in the field do not have clean ballast. They all have certain kind like fouling. A lot of fines accumulated in the track. This is the gradation analysis done by Professor Selig and Waters back in the 1990s and from the field data. The challenge is, can we characterize this kind like ballast gradation change along with shape property change in laboratory? Can we reproduce it? We find a solution is Los Angeles abrasion test. Actually, there are many different kind of tests proposed by different researchers before. Some said this works good, some said that works good. Recent findings based on Norwegian research, they said, like based on the monitoring of long-term behavior of the track and also the TRIAXIAL test, they find the TRIAXIAL test and the LA abrasion test correlated with each other to characterize the particle breakage, the particle gradation change very well. So we use the same approach here. We use abrasion test. We first put 10 kilos of the new ballast material into the drum and let it rotate in certain intervals. For limestone, we use 125 intervals, and for granite, we use 250. And then we do a detailed sieve analysis. We collect all the fines, all the materials, do not lose anything. And this is the gradation we can characterize in the lab. If you can remember the previous picture show the field data, those gradation changes are pretty much similar. And this is the way how we generate the fault ballast material in the lab. But still, we need a lot of materials to make a specimen to do TRIAXIAL test. Because each LA abrasion, we only can generate 10 kilos of materials, while for a TRIAXIAL test, we probably need a lot more. So that's why we repeated the LA abrasion test to about 13 times to totally generate 130 kilos of the fault ballast. This picture shows the different, they all start from the same gradations, but they end pretty much the same gradations after they reach a fouling index of 40. A fouling index is a parameter to quantify the fouling condition of the ballast. The average of the 13 gradations after LA abrasion test is the actual gradation we will use as the fault ballast gradation in the lab test later on. So this just to show you how the difference looks like with the new ballast and the fault ballast at the right side. There's one more gradation in the middle, and also we can see the picture there. The only difference between this picture and the picture on the right is whether we have the fine materials inside of it or not. In other words, for example, for the fault ballast material, we sieve all the fines, which is particles smaller than 9.5 millimeter or 3/8 of an inch materials out. We consider this kind of material as fines, which was recommended by Professor Selig and researchers before. This kind of like material is actually the fouling materials. So we get the fouling materials out, only left the larger particle inside to have this gradation. These particles are actually the particles will make the particle matrix or skeleton in the field without fines. The same way we characterize the different shape properties and use the same geometry to get the specimen. However, as we know, for the same geometry, since the gradation change, the shape property change, we will have different weight of the materials. The density is also changed. A lot of TRIAXIAL tests was try to have exactly the same density of different specimens. However, in the field, we will know the density of the field sample also change because of the continuous accumulation of traffic. This is why we keep the compaction energy the same, while density are different. This is show the strength test result. Surprisingly, we find the fouling, which is kind of unfavorable for the railway practitioners, is not a real bad thing in the lab. We find the strength test result for the fouled ballast materials is not necessarily lower than the new ballast. And on the contrary, for different confining pressures, in most of the case, fouled ballast is actually yield higher strength than the new ballast. So if I may rephrase what I'm saying is that with accumulation of traffic, the ballast actually gains strength instead of lose strength, although the gradation and shape property change significantly. But this is the case for the strength test. How about the case for the permanent deformation test? With different materials, we run the same permanent deformation test under the same condition, same loading pulse, same geometry. It's clearly we can say the permanent deformation behavior can be grouped into three, which is corresponding to different materials. When the particles get fouled, it actually will yield higher permanent deformation. While if the fines was not included, it will have less deformation, but still higher than the new ballast materials. So in this case, we can get an idea that if we have particles with finer materials, with more rounded and smooth particles, it will give us higher settlement potential. But if we have fines included, it will give us a higher settlement potential. So the fines is actually will lubricate the big particles, separate the particles from making effect contacts with each other. And then the same thing, after the lab test, we do the numerical simulation. By adequately addressing the particle shape, size distribution and shape property changes, we can capture the different materials response for the strength test. This one only show you the large particles of fouled ballast. The clean ballast was showed before. And also we do the permanent deformation test simulation. This one gives us much more closer result than the clean ballast. The reason of that is since we have more rounded and smooth particles, it will give us less sudden deformation of the particle assembly. While for the new ballast, we know it's very sharp, have a lot of sharp corners. If the sharp corners get ripped out or get abraded, it will give us kind of like a zigzag shape of the deformation. And also this is the average of 3. Try to give us an idea how to account for the variability of different initial assembly. And the next one is, how about we have water inside of it? What about if it rains? Will it change the properties of the ballast materials? But there's another question. How can we prepare these kind of materials to simulate when the ballast get wet? There are several approaches based on the literature. Somebody said, okay, let's just mix everything together. We will have big particles, we will have fouling materials, we will have water together. We mix them and compact. That's great. And someone else said, oh no, it's not that great. Let's just mix the ballast particles and the fouling materials together. And then at the end, we'll add water. This is another approach, which is also makes sense. And also, there's another approach. Someone said, why don't we just compact the ballast first? And then we will add the mixture of water and a fouling material together, and then just spread from top. This is also an approach. They all make sense for certain conditions happen in the field. But which one we will try to adopt? It's a question remains to us. So we propose a new approach, which think about the new ballast materials. It's free drain materials. If it rains or not, the water will go away. How about the foul ballast without fines? It's also a free drain material. So will the water influence that much? Probably not. The main problem is the fines. It's the fines who can retain the water inside of the structure and influence the overall behavior. So what we try to propose to do is we first mix the fouling materials, which is the fines, particles smaller than 9.5 millimeter or 3/8 of an inch, with certain water. This gives us a wet fouling materials. And then we will mix them together with the ballast, try to ensure every particle was coated with corresponding fouling materials, and then we'll compact it. So we did this in the lab. First, we have certain amount of the fouling materials, and then we mix it with water. Before doing any large-scale TRIAXIAL test, we did the Proctor test and also CBR test. Interestingly, we find the optimal moisture content for the maximum dry density for fines used in this study was about 9%. And there's a significantly drop on CBR values when the materials reach optimal moisture content. So we decided to use 3, 6, 9, 12% of the fines. This is the water content of the fines. It's not the water content of the overall materials. Follow the approach. We make the mixture first, which is the water and fines. And then we mix the wet fouling materials with dry ballast large particles. And then divide into 4 piles and use forklift to construct the specimen. How the result looks like is very counterintuitive. First one is a clean ballast settlement or permanent deformation behavior with no moisture. And then if we move to the foul ballast material without moisture, the permanent deformation gets increased, which is I already presented before. And then if I add, and then if I add fines, yes, it will still increase. The red dot will corresponding to each permanent deformation curves. When we add moisture, we are expecting it will hurt or jeopardize the performance of the ballast materials, while counterintuitively, with 3% of moisture of the fines, is actually help to stabilize the structure. It actually gives us less permanent deformation than the foul ballast materials. How about 6%? It gives us even less permanent deformation. How about 9%? Would it give us the same behavior as the clean ballast material, which is the new ballast particles? Oops, no. It gives us the highest settlement. How can that happen? Our explanation is, since we did the CBR test with 3% moisture content and 6% moisture content, these are all unsoaked CBR tests. It's actually under certain threshold of moisture content of the fine particles. It still gives us a high suction potential. That's why it behaves like stabilize the whole structure. However, if you let the moisture content of fines beyond certain threshold, it will reduce the suction potential, which means the fine material will lose its strength first and then behave like a slurry or something to separate the big particles, kind of like a lubrication effect. Will the strength test give us the same behavior like this? Will 3% moisture content of fines or 6% moisture content of fines give us higher strength result than the clean ballast, and then the 9% give us the least? Will that make sense? Yeah, it might be, but the result is also different from what we thought. No matter what kind of moisture content of fines you have, it significantly drop the strength. How can that happen? Why in strength test case, the moisture with the fines cannot stabilize the whole structure? Yes, similar findings was found based on the literature. So the explanation of this kind of phenomenon is when you have small strands, which is equivalent to like permanent deformation test, the suction potential can play an important role. However, for large strand, for example, in this case, strength test up to 10%, this will actually have a lot of localized saturation of the particles. When you have large strands, when the particles get pushed with each other, it will have a lot of localized saturation situation. So the particles get loose and loss of the suction potential. And that's the reason how this happens. So that's pretty much the new stuff as compared with what I have done in the last presentation. With that, that's all I have to present today. I will acknowledge my sponsors, Federal Railroad Administration, Geosynthetic Institute, and Transportation Technology Center. I haven't mentioned anything with the geosynthetic reinforced one, but if you are interested, we can talk about it later. And I have to acknowledge a lot of friends who contribute to this study. And that's it. Thank you so much. And any questions? Oh, run out. It's too boring, or you don't give it. Okay, I don't believe you.
So, just two quick, one question, one comment. The test that you're running, is this a drained or undrained?
It's undrained. Well,
so how do you
we didn't seal the specimen. We didn't seal the specimen. So we just mix the water with the fines first. It's actually the water content of the fines. It's not the water content of the whole structure. So it's kind of like wet material.
About the saturation percentage of the entire structure?
It's not a saturated sample for the entire structure. It's only the moisture content of the fines. Yeah. We kind of like have a wet fouling material and then added them and mix with the larger particles and then compact the whole thing. Yeah. I don't think it's a saturated specimen. And even if we have large strands, it only have local saturation. Yeah, but another thing I didn't mention here, I haven't presented the result from 12% moisture content of the fines. The reason is that we try to build a sample with 12% of moisture content of the fines. But however, after compaction, as we detach the mold, the specimen cannot stand on itself. So it really collapses. It's because the moisture content is already beyond a certain threshold. So it loses its suction potential, cannot stand by its own weight.
But when you compact those specimens at different moisture content, you compacted everything at the optimum moisture content? What density were you trying to achieve when you compact the specimens?
Okay. For the optimal moisture content is 9%, which is for the fines. It's not for the big particles.
What the big particles?
What?
I think there's questions about the ballast.
Yeah, the ballast. When you compacted them, for example, were they all at the same compacted at the same compactive effort, or
same compaction effort?
So
the density will be different.
Okay.
Yeah. For the clean ballast material, it's 68. For the 68 kilos for the specimen. For the foul ballast with fines is about 98 kilos. For the gradation without fines, but only degraded particles, large particles, it's about like 73 kilos, so if I remember correctly.
You may very well maybe having a higher density in your low moisture content situation that might be maybe changing your permanent deformation resistance.
Yes, the density can definitely play a role. Yes, yes, but this is what happened in the field. Yeah. If you look at in the field, the track will keep compacting the ballast, which causes the ballast. This is one reason the track will have geometry problem, is because the track thickness will get reduced, while at the meantime, the density get increased. And the comment?
Comment was about your title of your presentation.
Okay.
What was it?
Multi-scale framework.
But there was something else in there.
Life cycle.
Life cycle.
Yeah.
So that usually, leaves a perception about, when you say life cycle, it starts from the production of the quarry materials, transportation. So that life cycle gives a different impression. This is more of a service life analysis of
yes,
ballast
yeah,
materials.
yeah. I agree with you. It's more like service life.
When I heard life cycle, I thought you were gonna do the same thing Rebecca and Songa was working on the life cycle.
I'm not as good as them. yeah. We mean like a service cycle from day one to the end. The reason we choose the Fouling index of 40 of ballast material is because Fouling index of 40 is the indicator of when we need to replace the particles. It needs immediately maintenance activities. Yeah, you're right. We mean a service life cycle or service cycle.
So the material that you used at the wet condition was limestone ballast, right?
Yes, all the result present here is limestone.
So what is the rough plasticity of the fine when you add water?
It's
9%, do you think if the fines are plastic?
Yes, the fines are generated based on the LA abrasion test, which is not a plastic fines. It's all limestone. It's non-plastic.
So if you have some material that has plastic fines, are you expecting to see the same trend in terms of demand deformation?
I don't expect to see the same trend if the material is changing from non-plastic to plastic. However, similar studies was done before to use a fouling agent instead of use the fouling material degraded from the original ballast. Like they can add coal dust, they can add mineral filler, they can add clay, they can add whatever they want. However, this is not the main case to cause ballast fouling in the track. The main case to cause ballast fouling is from ballast degradation.
So the material may generate plastic fines by itself, right?
What kind of material will generate plastic fines? You think limestone will generate plastic
Not
fines?
limestone, but some other type of aggregate or something.
Well, if the aggregate has plasticity itself, yes. If the particles is made from clay, yeah, of course, it will generate clay.
And then that, like, the decreasing the permanent deformation that you showed may not happen, right?
What do you mean?
Increasing the permanent deformation will happen. I mean, this structure may not get stable the way that you were saying that at some point.
Whether the structure gets stable or not based on the global metrics of the structure. Like if we have little bit of fines, in my mind, it will stabilize the structure. However, if you have excess amount of fines, it will prevent the large particles to form a stable matrix, which will act, instead of a stabilizer, it will act as a lubrication to separate the big particles.
Even at the wet conditions?
Even at the wet condition? Wet condition is a different story than the matrix, right? Wet condition is when the fine materials get stronger or get weaker. Did I answer your question? Any more?
Not exactly. But just my point was that can we generalize it to all kinds of material?
No. I can only make a statement based on what I have done, which is limestone. I cannot make a statement to judge the other materials. I can only make assumptions.
Let me make a comment on it. What is the most used material in the railroads for the railroad ballast material?
Granite, trap rock, and limestone.
Okay, do you expect for the fines of those materials to be plastic if they are abraded in the field?
I don't expect the same.
Okay.
Yeah, so most of the fouling case, they generate non-plastic fouling materials. Unless in some case, if you want to have plastic fouling materials, you just dump your coal into the ballast track, then you have plastic. Because the coal dust is plastic.
Plastic material might come from the subgrade itself due to pumping, but this is, in the United States especially, where we have heavy axle load due to freight trains, many fallen material is usually from the aggregate itself. It is around 70%, I guess.
It's around 76%.
In Europe, the most of the fallen material comes from subgrade itself because they use high-speed trains. It is not that heavy. It doesn't abrade material that much. that might be a study that, I mean, interest Europe, but actually not the freight companies in here.
This could be a good topic for you to continue up this study. That's it. Professor, do you have any comment?
We were just talking about coal dust. Whether you make this thing coal dust.
Uh-huh.
Did you run that? Did you?
I did not run actually. Dr. Mavoni ran it.
I haven't run a triaxial test on a power sample coal dust. I just did some kind of like elasticity test.
I'm just curious if the coal. Yeah, it seemed like it would be more plastic though, potentially.
Yeah, because the plastic faults was studied extensively. However, it's not the main cause of the fouling reasons. Like even Haihuang was did like direct shear with the coal dust fouling. But when they prepare the materials, they typically just use the water content of the overall specimen, which can easily get a conclusion, which will increase the water content. It will further reduce the performance or jeopardize the performance. However, we just try to use the moisture content of the fines of the fouling materials. Yeah, it's actually a question was raised by the Australian heavy haul railway, because some of them are saying we don't expect like bad performance when we have a little bit of fouling, and we don't expect a bad performance when we have a little bit of rain. So this is the motivation we continue in this study. But when the track gets flooded in the field, it definitely will lose its strength. Okay, thank you. Thank you for your time.